There are moments in human history when the impossible becomes inevitable, when the fantasies that lived only in the margins of science fiction suddenly materialize under the cold fluorescent lights of reality. For a century, light speed was that boundary, the ultimate wall that separated our dreams from our destiny. It was the cosmic speed limit, enforced by the universe itself, guarded by equations so elegant and so absolute that to challenge them seemed like madness. And yet, in a quiet NASA facility on a Tuesday morning that felt like any other, that wall came down. Not with explosions or fanfare, but with a whisper. A single admission that rewrote everything we thought we knew about motion, space, and the very fabric of existence itself. The disbelief came first. Scientists who had spent lifetimes accepting Einstein's immutable laws suddenly faced a truth that seemed to violate every principle they'd been taught. Then came the awe, that slow, creeping realization that humanity had just taken its first step beyond the prison of conventional physics. The key was hidden in a paradox so simple it had been staring at us for decades. You cannot go faster than light, but space can. Those 7 words became the foundation of everything that followed. They weren't breaking the rules. They were learning to play a different game entirely. In a sterile laboratory bathed in cold blue light, surrounded by machines that hummed with barely contained energy, history bent without making a sound. The scientists stood motionless, watching readouts that defied belief, holding their breath as if afraid that exhaling might shatter the miracle. Because what they had created wasn't just a propulsion system, it was proof that the universe had been keeping secrets, and humanity had finally learned how to ask the right questions. Albert Einstein didn't just give us relativity, he gave us a cage. In 1905, his special theory of relativity established that nothing with mass could reach the speed of light, 299,792,458 meters per second. It wasn't a suggestion or a technological limitation. It was cosmic law, written into the mathematics of space-time itself. As objects approach light speed, their mass increases toward infinity, requiring infinite energy to push them further. For over 100 years, this wasn't debated. It was simply accepted as the fundamental architecture of reality. But acceptance never stopped humanity from dreaming. Throughout the 20th century, science fiction writers like Arthur C. Clarke and Isaac Asimov imagined warp drives and hyperspace, inspiring generations of physicists who secretly wondered if the universe might have loopholes. Star Trek's USS Enterprise bent space around itself. Dune's Guild navigators folded space-time like origami. These weren't just stories. They were thought experiments wrapped in entertainment, mathematical puzzles disguised as adventure, and buried within them were seeds of genuine theoretical physics, waiting for the right minds to cultivate them. NASA's legacy was already monumental before this moment. They put humans on the moon when computers had less power than a modern calculator. They sent Voyager probes beyond our solar system, carrying messages to civilizations that might never exist. They launched the James Webb Space Telescope, peering back to the dawn of creation itself. Each achievement pushed the boundaries of what seemed possible, turning yesterday's impossibilities into today's accomplishments. But those were incremental victories, expanding our reach within the existing rules. What NASA was about to reveal wasn't incremental. It wasn't another telescope seeing farther or another rocket burning hotter. It was a complete paradigm shift, a fundamental reordering of what travel itself meant. This wasn't just the next chapter in space exploration. It was the beginning of an entirely new volume, one where the stars stopped being distant points of light and became destinations we could actually reach within a human lifetime. The press briefing began like hundreds before it. Journalists filed into the auditorium at NASA's Jet Propulsion Laboratory, expecting updates on Mars rovers or budget discussions. Instead, they walked into a moment that would fracture history into before and after. The atmosphere was strange, a thickness in the air that came not from tension, but from barely contained enormity. Senior scientists who normally maintained clinical detachment sat at the podium with expressions of quiet reverence, as if they'd witnessed something sacred. When Dr. Sarah Chen, Director of Advanced Propulsion Systems, began speaking, her voice cracked on the third word. She steadied herself, glanced at her colleagues, and delivered the statement that would echo across every media platform on Earth within minutes. We have successfully created and tested a propulsion system capable of achieving effective velocities at or near the speed of light. The silence that followed wasn't confusion. It was the sound of reality reorganizing itself. Journalists' hands froze over keyboards. Cameras continued recording, but the operators had forgotten to breathe. Dr. Chen continued, explaining that this wasn't theoretical anymore. They had built it, tested it, I watched it work. She described how a small-scale prototype had disappeared from one point in space and reappeared at another, covering a distance that should have taken minutes in what could only be measured as instantaneous. Veteran NASA engineers, men and women who had spent 40 years launching humanity's dreams into the void, sat in the front row with tears streaming down their faces. One of them, later interviewed, could only whisper, "We did it. We actually did it." But the questions immediately erupted, desperate and disbelieving. How? What exactly had they built? How does it work? Dr. Chen smiled, a strange, knowing smile that contained decades of classified research, and said simply, "We didn't break physics. We learned to dance with it." The briefing ended not with answers, but with an open loop that would consume the scientific world. Humanity had just achieved light speed, but the story of how was only beginning. The answer lay in space-time itself. Einstein showed us that space and time aren't separate entities. They're a unified fabric that can be warped by mass and energy. Massive objects like stars bend this fabric, creating gravity wells. But what if you could manipulate that curvature artificially? What if you could compress space-time in front of you and expand it behind you, creating a wave that carries you forward while you remain stationary within a bubble of normal space? You wouldn't be moving faster than light. Space itself would be moving, and you'd be surfing the geometry. This concept wasn't new. In 1994, Mexican physicist Miguel Alcubierre published equations describing exactly such a mechanism, what became known as the Alcubierre drive. His mathematics were elegant and theoretically sound, but they required exotic materials with negative energy density, amounts of energy equivalent to the mass of Jupiter, and technologies that seemed forever beyond reach. For 30 years, the Alcubierre drive remained a beautiful impossibility, discussed in academic papers but dismissed as impractical. NASA's engineers didn't dismiss it, they obsessed over it. The breakthrough came from understanding that you don't need to warp space dramatically across light years. You need to create a stable bubble, a localized region where space-time curvature is controlled with precision. Inside this bubble, physics remains normal. The ship experiences no acceleration, no time dilation, no lethal forces. But the bubble itself displaces through folded geometry, essentially sidestepping the light speed barrier by changing the playing field. The ship doesn't move through space, it moves space. The first small-scale experiment happened in a facility in Nevada at 3:47 a.m. on a morning nobody was supposed to remember. A cylindrical test craft, barely larger than a refrigerator, sat suspended in a magnetic field. When the field generators activated, creating the theoretical warp bubble, the craft didn't accelerate. It didn't blur. It simply ceased to exist in one location and existed in another, 100 meters away. Scientists watching the readouts couldn't process what they'd seen. They ran the experiment 17 more times that night, each success igniting a wonder that bordered on religious experience. The universe had just revealed it was far stranger and far more permissive than anyone imagined. What the public saw in that press briefing was the conclusion of a story that began in classified research facilities over a decade earlier. Behind closed doors, under code names like quantum field analysis and high-energy propulsion research, a small team of physicists, engineers, and mathematicians had been chasing what most considered a ghost. The funding came quietly, buried in defense contracts and obscure line items in NASA's budget. If they succeeded, it would be humanity's greatest achievement. If they failed, it would be the most expensive embarrassment in scientific history. The secrecy wasn't about military advantage. It was about protection, from ridicule, from premature publicity, from the crushing weight of expectation. The scientists involved knew they were pursuing something that violated common sense. Mainstream physics dismissed warp drives as interesting mathematics with no practical application. Publishing their work early would have meant career suicide, funding cuts, and endless ridicule from peers who couldn't see beyond conventional limitations. So they worked in silence, troubleshooting impossible problems, failing hundreds of times, watching calculations that should work crumble against experimental reality. Anonymous sources later revealed that inside NASA, the project had an unofficial name, Genesis. Not because it was about creation, but because it represented a new beginning, a departure from everything that came before. The team became almost cultish in their dedication, working 18-hour days, sacrificing personal lives, driven by the tantalizing possibility that they might be the ones to crack the code. Marriages ended. My health declined, but they persisted because some problems demand everything you have. The breakthrough came from solving the negative energy problem. Traditional Alcubierre physics required exotic matter that probably didn't exist. NASA's solution was ingenious. Instead of generating negative energy directly, they learned to manipulate quantum vacuum fluctuations, the constant creation and annihilation of particle-antiparticle pairs that occur even in empty space. By precisely controlling these fluctuations, they created regions of effective negative energy density without violating any laws of physics. When the first stable warp bubble held for more than a microsecond, the lead engineer simply sat down on the laboratory floor and wept. Project Genesis had succeeded. The universe had opened a door. They called it the Quantum Flux Field Drive, the QFD. At its heart was a mechanism so precise it had to be calibrated to within quantum uncertainties. The drive doesn't push against anything. It doesn't expel mass or burn fuel in any conventional sense. Instead, it creates a controlled distortion in the quantum vacuum, generating a stable warp bubble approximately 50 meters in diameter. Inside this bubble, spacetime remains flat and normal. Outside, spacetime curves according to precisely calculated geometries, compressed ahead of the craft and expanded behind it. The physics are almost poetic in their elegance. The QFD taps into zero-point energy, the fundamental energy that exists in quantum fields even at their lowest possible state. By manipulating these fields with exotic electromagnetic configurations, NASA engineers created regions where space-time curvature becomes malleable. It's not teleportation, it's not magic. It's controlled surfing on waves of geometry, using the universe's own structure as the medium of travel. The craft doesn't experience acceleration because it's not accelerating. Space is flowing around it while it remains at rest within its protective bubble. The key innovation was the quantum harmonic regulator, an AI system so sophisticated it makes real-time adjustments thousands of times per second. Maintaining a stable warp bubble is like balancing on the edge of a knife while the knife is made of mathematics. The slightest imbalance could collapse the bubble or, worse, create uncontrolled space-time distortions. The QHR monitors quantum field states, energy distribution, and geometric stability simultaneously, making corrections faster than any human operator could perceive, let alone execute. It's the difference between theory and reality, the engineering that transforms beautiful equations into functional miracles. The visual description from witnesses is almost mystical. When the QFD activates, the craft becomes surrounded by a halo of blue-white light, Cherenkov radiation from particle interactions at the bubble's boundary. For a moment, the ship seems to shimmer, as if viewed through heat distortion. Then it simply isn't there anymore. No sound, no flash, just absence. And somewhere else, light years away or meters away depending on the field configuration, it reappears in exactly the same state it left. Inside, passengers would feel nothing. No acceleration, no vibration, no indication that they'd just traversed distances that should take centuries. The universe moved around them and they arrived. The announcement didn't just shock the scientific community, it fundamentally altered humanity's trajectory. Within weeks, NASA's mission statement was rewritten. The new philosophy spread through every department like wildfire. We don't escape gravity anymore, we sculpt it. This wasn't exploration within limits. This was the breaking of the final chain, the moment when humanity stopped being confined to one small corner of one galaxy and became something capable of touching the cosmos itself. The practical implications unfolded rapidly. Teams immediately began designing interstellar probes to Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away. With conventional propulsion, that journey would take 40,000 years. With the QFD, it became possible within years, perhaps even months, depending on how aggressively they pushed the warp field geometry. The Alpha Centauri system, with its potentially habitable planets, transformed overnight from a distant dream into an achievable destination. Scientists started reimagining communication protocols because signals traveling at light speed would no longer be the only way to send information. You could send the information itself, carried by ships moving at effective light speed. Physics textbooks became immediately obsolete. Universities scrambled to update curricula, adding entire new courses on warp field mechanics and space-time engineering. Students who had been taught that interstellar travel was impossible for any practical civilization now learned that those limitations had been technological, not fundamental. The psychological shift was staggering. An entire generation suddenly realizing they might live to see humanity establish colonies beyond our solar system. At NASA headquarters, the mood was electric. Engineers gathered around holographic displays showing updated mission architectures. Mars became a stepping stone rather than a destination. The Kuiper Belt became a neighborhood. Light years, those impossible distances that made the universe seem so vast and lonely, collapsed into manageable journey times. One scientist described it perfectly. We used to measure space and how long it would take to get there. Now we measure it in geometry. How curved is the path? The stars weren't distant anymore. They were just on the other side of a properly warped piece of space-time. The second space age had begun, and this time, the entire universe was within reach. The beautiful irony is that Einstein wasn't wrong. His equations still hold with perfect accuracy. The speed of light remains the cosmic speed limit for objects moving through space. What NASA discovered wasn't a violation of relativity. It was a loophole hidden in plain sight within relativity itself. General relativity explicitly allows space-time to warp, compress, and expand. There's no law preventing space itself from moving faster than light. The universe did it during cosmic inflation, black holes do it at event horizons. NASA just learned to do it controllably, on demand, in a laboratory. The reconciliation between relativity and quantum field mechanics through warp geometry represents the most significant theoretical development in physics since quantum mechanics itself. Physicists had long struggled to unite Einstein's smooth, continuous spacetime with quantum mechanics' discrete, probabilistic fields. The QFD doesn't solve that fundamental incompatibility, but it reveals a middle ground where both frameworks cooperate. You can't quantum tunnel faster than light, but you can quantum engineer the geometry through which light travels. It's a distinction that seems subtle but changes everything. Velocity becomes a meaningless concept in this context. The ship inside the warp bubble isn't moving at all relative to its local spacetime. It's at rest. The bubble itself isn't moving faster than light. It's a region of spacetime that's disconnected from the surrounding geometry. The craft arrived at its destination not because it traveled fast, but because the definition of distance was temporarily rewritten. It's not speed, it's topology. Einstein's field equations got a silent amendment, not broken, not discarded, but expanded. The new equations include additional terms accounting for artificially induced curvature, controlled exotic energy states, and engineered quantum vacuum configurations. Textbooks added chapters. Research papers flooded journals. The Nobel Committee started receiving nominations before the year ended. But beyond the mathematics and the accolades was something deeper, something almost metaphysical. Humanity's understanding of motion itself had been fundamentally reinvented. We didn't learn to go faster. We learned that going was never the point. The point was arriving, and the universe had multiple paths. We'd just discovered one that ignored the conventional route entirely. Behind closed doors at NASA's Ethics and Philosophy Integration Office, a department that suddenly became critically important, dozens of philosophers, physicists, and ethicists gathered for emergency sessions. The question wasn't whether humanity should use this technology. That ship had sailed the moment the first warp bubble stabilized. The question was, what does it mean to have power over space-time itself? For the first time in history, humans could manipulate the fundamental structure of reality in ways that went beyond chemical reactions or nuclear forces. They could reshape geometry. The fears were profound and legitimate. Every warp bubble creates ripples in space-time, minute distortions that propagate outward. The effects seem negligible, but what happens when thousands of ships create thousands of bubbles? Could humanity accidentally destabilize local space-time structure? Could cascading distortions create permanent scars in the fabric of reality? One theoretical physicist presented calculations suggesting that the universe might remember each warp event, accumulating a kind of geometric fatigue. Nobody knew if this was paranoid speculation or genuine danger. The philosophical implications spiraled outward. Dr. James Morrison, a former priest turned cosmologist, posed the question that kept everyone awake. We used to reach for the stars. Now we move them, or at least the space between us and them. Have we crossed from exploration into manipulation? Are we architects now, or are we vandals? The religious communities were divided. Some saw it as humanity fulfilling its divine mandate to master creation. Others saw it as hubris, a Tower of Babel moment where we'd reached too far and would inevitably face cosmic consequences. The haunting imagery came from one of the senior engineers. During a late-night session, exhausted and philosophical, she described watching the readouts during a test flight. Every time we warp, we're essentially tearing a small hole in spacetime's fabric and then stitching it back together. The universe heals itself, but we don't know if there's a limit. What if we use this so much that reality develops scars? What if one day space just remembers too much and refuses to bend anymore? The silence that followed that statement was total. They had created a miracle, but miracles come with responsibility. And some responsibilities are too large to fully comprehend until you're already bearing them. Within months, the ripple effects transformed human culture at every level. Children started drawing pictures of warp ships instead of rockets. Artists created installations exploring curved spacetime, using light and sculpture to represent geometric concepts that were once purely mathematical. Philosophers wrote treatises on what it means to be a multi-star civilization. The stars stopped being decorative points in the night sky and became real places with real coordinates, accessible within human lifetimes. The psychological shift was seismic. Loneliness transformed into anticipation. Space travel evolved into something unrecognizable from its previous form. Navigation became an exercise in pure geometry. Pilots didn't plot courses through distance. They mapped curvature. The new training programs at NASA focused on understanding space-time topology, recognizing stable geometric configurations, and interpreting quantum field states. Journey times stopped being calculated in years and started being measured in warp cycles. How many bubble compressions and expansions would be needed to reach a destination? The mathematics were complex, but the principle was simple. You don't travel to the stars. You bring yourself and the stars closer together, then let go. The poetic irony wasn't lost on anyone. For centuries, humanity defined progress by how fast we could move. Faster horses, faster cars, faster planes, faster rockets. We were obsessed with velocity, with pushing against limits, with raw speed. But the QFD revealed that we'd been asking the wrong question all along. The universe wasn't about speed. It was about geometry, about topology, about understanding the landscape of space-time itself. We didn't conquer light. We learned to flow with the structure of reality, to work with cosmic architecture rather than against it. The breakthrough wasn't power, it was humility combined with intelligence. In that quiet NASA laboratory where it all began, now designated as a historical landmark before the paint had even faded, a single moment captured everything. The main lab remained operational, still running experiments, still pushing boundaries. But late at night, when only security guards and obsessive engineers remained, you could stand in the observation room and feel it, the hum of the warp field generators cycling through calibration tests. It was barely audible, more vibration than sound, but it resonated with something primal. That hum was the sound of possibility becoming reality, of mathematics becoming motion, of humanity becoming something larger than a single planet species bound by conventional physics. The observation window looked out onto the test chamber where the prototype QFD sat dormant, waiting for the next experiment. In the reflection of that glass, you could see both the machine and the stars beyond through the facility's observatory dome. Past and future, merged in one image. And in that moment, you understood. The universe hadn't just opened its gates. It had been waiting all along for us to realize the gates were never locked. We just needed to stop trying to break through them and learn to step through the geometry instead. The journey to the stars wasn't about reaching them. It was about understanding that in a universe of curved spacetime, reaching and arriving were always the same thing. We just needed the wisdom to see it and the courage to bend space to match our vision. The age of light-speed travel hadn't begun. The age of geometric navigation had arrived, and with it, humanity's true destiny among the stars.